Okay, here application of simple harmonic motion and how the here one of a vertical spring you can see here one of a vertically attached spring is here. This one is a spring which is fixed with this is the rigid support. This is a one of a is light spring. Here is also light spring. This is also light spring. You can see here the vibration of a particles in a light in a vertical string spring, that is it is a spring. You can see all these are the spring. You can see the figure A, this is not attached with the mass m and this is attached with mass m and this one is also attached with mass m. You know that this is freely suspended at that time. Here is suppose it has length, a spring has length. You can see here A and this is the rigid one, rigid support with to which this one is suspended, and you can see here, and this one is another L. When it gets displacement L, this mass at that time you can see the how it gets extended. You can see this spring here, and initially it is at this position B. When it is suspended with this mass M, then it goes from B to C position. You can see it, and at that time it displaces L distance. So you can see here at, and again it is displaced by another restoring force, displaced by some force. It again gets displacement Y, and at this position how much it has restoring force. We are going to calculate F1 equal to minus KL, and how much restoring force for this case, second a third, you can see, which would be F2 equal to minus K L plus Y, and when we subtract restoring force in it from restoring force what we have in this case, we get net restoring force. So how it is arranged here in an experiment, you can see here, and I have explained all these things. What you can see in this figure, here you can see all their arrangement, all here whatever you can see arrangement I have written here at. Let's get started. Let us consider mano a light spring hanging on the rigid support A. Rigid support A ma light spring A लाई hanging गरेको छ, whose lower end lies at a point B. Lower end P मा lies गरेको छ. When the mass M is attached to the lower end of a spring, जब lower end मा M मा चाहिँ mass लाई attach गरिन्छ, then the mass is displaced by B, from the B to C, where extension produced on a spring is L and the restoring force on a spring is F1 equal to minus KL. जब M mass यसमा hanging यसमा चाहिँ attach गरिन्छ lower end मा, त्यतिखेर F1 restoring force हुन्छ र L distance जब चाहिँ यसले displacement हुन्छ यहाँबाट B बाट C मा पुग्छ, त्यतिखेर F1 equal to minus K L1 L हुन्छ, जहाँ चाहिँ K is restoring constant भन्छ, constant नै हो restoring constant force. अब यो चाहिँ minus sign indicates that force always acting toward the mean position. You know that it is restoring force is always in the opposite direction of a displacement. Suppose here object is going down and restoring force is in a up direction. That means which is in a opposite direction. And the next one is when the this is about the the third figure, when the spring is again displaced by a length y. जब यो स्प्रिङ लाई अझ y length ले डिस्प्लेस गर्यो भने m mass displaced from C to D. यहाँ C पोजिसन मा थियो, यहाँसम्म C पोजिसन मा आएर त्यो D मा पुग्यो. त्यसपछि then released the m mass starts here. The small this one is mass m starts to move in simple harmonic motion. त्यसपछि simple harmonic motion मा move हुन थाल्छ. Then restoring force on the extension of a spring L plus y. अगाडि यहाँ L distance displaced भइरहेको थियो, यहाँ y distance displaced भयो भने F2 equal to minus K L plus y भयो. अनि त्यसपछि नेट रिस्टोरिङ फोर्स इक्वल टु F2 minus F1. यो F2 को भ्यालु K L plus y, त्यही भएर K L plus y minus F1 भनेको चाहिँ minus KL. From here minus KL I have written here. When you know the minus plus sign, you balance, you can cancel this KL and you have here F equal to minus KY. This is the total restoring force which is in this spring. And if the A is the acceleration on the mass M mass मा चाहिँ A acceleration produce भयो भने F भनेको त MA हो, त्यही भएर MA यसमा राख्यो अनि इक्वल टु A लाई एक्लै छोड्यो भने यो M चाहिँ D डिभाइडमा जान्छ, a बराबर माइनस k बाई m, y हुन्छ माइनस साइन छ i। अब यो अगाडि एक्सप्रेसन सिम्पल हार्मोनिक कुनै पनि अब्जेक्ट सिम्पल हार्मोनिक मोसनमा छ भने त्योसँग a इक्वल टु माइनस ओमेगा स्क्वायर y हुन्छ। यो चाहिँ एक्सप्रेसन अगाडि नै हामीले क्याल्कुलेसन गरिरहेको छ। अब यो दुईटा इक्वेसन 1 र 2 लाई कम्पेयर गर्ने, y इक्वल टु y, a इक्वल टु y, a इक्वल टु a, k बाई m इक्वल टु अब ओमेगा स्क्वायर y, ओमेगा स्क्वायर हुन्छ, त्यही भएर ओमेगा स्क्वायर यहाँ देख्दै हुनुहुन्छ कम्पेयर गर्ने। ओमेगा स्क्वायर इक्वल टु माइनस k बाई m, माइनस माइनस क्यान्सल, ओमेगा स्क्वायर भएको हुनाले यहाँ अंडर रुट भयो k बाई m। यसलाई उल्टा गरेर if t इज द टाइम पिरियड अफ द पार्टिकल्स को t टाइम पिरियड भयो भने अब ओमेगा को फर्मुला हुन्छ 2 पाई बाई t इक्वल टु यहाँ k बाई m यही हो। अनि यसलाई उल्टा पार्यो भने m बाई k हुन्छ, अनि क्रस मल्टिप्लाई गरेर 2 बाई d अंडर रुट m बाई k। अनि के t भनेको टाइम पिरियड of the time period of the particles in vibrating spring vibrating vertically vibrating गरेको स्प्रिङ मा भएको पार्टिकल्स को टाइम पिरियड हो भने t बराबर जहिले पनि 2 पाई अंडर रुट m बाई k हुन्छ। यतिबाट टाइम पिरियड निकाल्न सकिन्छ। यो एउटा एप्लिकेसन भयो। अर्को चाहिँ सिम्पल पेन्डुलमको छ, नेक्स्ट डे चाहिँ एक्सप्लेन गर्छौं। थ्यांक यू।